initially, because we're starting with N2O4 as our reactant, we have a high concentration of N2O4 and 0 in terms of the concentration of NO2. The concentration of N2O4 decreases, the concentration of NO2 increases, and eventually the rate of change, the rate of decomposition of N2O4, the rate of formation of NO2 becomes the same. So the rates are now the same. We can say that at the particular point when the rates become the same is exactly where equilibrium is achieved. Okay. And what that looks like in terms of concentration is this figure. So we have the concentration of N2O4 decreasing, the concentration of NO2 increasing. And why don't they end up as the same line for the concentration? Yeah, so why is NO2 greater concentration than N2O4? Yeah?
You're producing 2 NO2s for each singular N2O4.
Yes, we're producing 2 NO2s for every N2O4. That's the stoichiometry. Okay? So the concentration at equilibrium of NO2 is twice that of N2O4. Okay, very good. Again, where the concentration is no longer changing on this plot for the species, that's where we've achieved equilibrium. So I mentioned that the rates are the same at equilibrium, at dynamic equilibrium. We can use our rate laws to write we can write the rate laws for this. So for the forward reaction, we have rate equals K sub F times N2O4. So going from N2O4, that's the reactant to form NO2. For the reverse reaction, rate equals K sub R, NO2 squared. Don't forget, well, this is an elementary reaction, I guess I should say that. So we can square this concentration in the rate law. By definition, we have dynamic equilibrium, and so the rates are equal. And so we can set these two equations equal to each other. So K sub F times N2O4 equals K sub R times NO2 squared. Okay? We kind of did this when we were looking at reaction mechanisms, and we said we had a fast first step. You can set, if it's in equilibrium, you set the rates equal to each other. That's what this is. But we can also do one more manipulation from this. And we are going to divide both sides by N2O4. We're going to have K sub F. Hang on, let me do it this way, and we'll do it in one step. Let's divide both steps by N2O4 concentration. And also divide by K sub R. So basically, I'm taking our rate constants, putting them on one side of the equation, and putting their concentrations on the other. So we have K sub F over KR equals NO2 squared over N2O4. And what we do with equilibrium is we basically say that this is equal to some constant. And we use uppercase K. Sometimes we use K sub C. We use K sub C when we're working with aqueous solutions. So basically we're taking our rates, we're taking our rate constants, grouping them together, calling that a new K. That's our equilibrium constant. This equilibrium constant, we're going to be working with these for the next several weeks. Okay, they are going to tell us about an equilibrium reaction. Does it favor the product side? Does it favor the reactant side? What happens when we have two reactions with rate constants? How does that affect, and there's happening simultaneously, how does that affect the overall equilibrium? Things like that. Okay. Questions? All right. Let's do a demo. I'm going to need 2 volunteers to come down here and play with these. Come on down. One more. Come down, Brady. Lucy? Everyone, Lucy and Braden. Okay. So, here's what's going to happen. Braden, do you want this side?
Sure.
Okay, don't finish. So, we are going to assume that this is our reactant, these are our products, and the process of the amount of beads are proportional to the amount of reactants or the amount of products. So right now we have all kinds of reactants and we have no products. We're going to make this reaction happen by grabbing a cup full of beads and scooping it into the product side. And then Lucy, you are going to start, we're going to do this simultaneously. You're going to scoop from the product side back into the reactant. So that's our dynamic equilibrium.
So it's a race.
It's not a race. Definitely not a race. You have to do it together. You're going to have a very boring start, but act it out for us. Okay? So the scooping equal, and that's going to be our equal rate. So you have to do it at the same time. Where are we going to end up? Here. How many products will we have? Tell me when to stop. Okay. About halfway. I feel like that was a Price is Right. You know, we need that guy that walks up the mountain song. Okay. All right. Let's see. Are you ready? Let's do a countdown.
Yeah.
3, 2, 1, scoop. These guys are fast. How are we doing? Let me know when it's not changing anymore. You all have a better view. Is it changing?
It's not changing.
Not changing. Okay, you can stop. All right. Steven, thank you. You guys got Steve. Thank you. So we got to a point where the rates were certainly equal. The number of products being added back to the reactants was equal to the number of reactants added to the product side. But this isn't where you expected it to end up, is it? How do you think we could change that? Yeah. Size of the cups. Yeah. So the size of the cups will dictate our equilibrium level. I don't know how to parallel that to what happens in real life, but that's just how it's happening here. I guess maybe that's, yeah, I got that. But yeah, so slightly different than what you maybe expected. But the idea is that the rates are the same. We've reached equilibrium, and it's a fun game, right? Cool. Questions on that? Is that a question? No. Okay. Okay. So Again, we're thinking about concentrations of reactants and products. We're going to relate those to an equilibrium constant. We can write an equilibrium constant expression for every equilibrium reaction. And the sort of general way of writing this, so if we have our reaction A plus B in equilibrium with D plus E, we can write our equilibrium constant is equal to the concentration of products raised to their stoichiometric coefficients over the concentration of reactants raised to their stoichiometric coefficients. So D raised to D, E raised to lowercase e, A raised to lowercase a, times B raised to lowercase b. So in general, that's how you write an equilibrium constant expression. Relatively straightforward, right? Okay. Products over reactants, raised to their stoichiometric coefficients. So take a second, write down the equilibrium expression for this reaction, A plus BC in equilibrium with AB plus C. So everything has a stoichiometric coefficient of 1 in this equation. So we'll take the concentration of products, AB, times the concentration of C, divided by the concentration of A times B times BC. Everything raised to the power of 1. Okay. Do we have to do K sub P? Because everything's in the gas phase. So K sub P is an equilibrium constant expression that we can write for gases. But we can also use K sub, not equal to, can use K sub C for gases as well. In general, I'm just writing, in this example, just writing K, so that we get good practice setting up concentrations of products. Yeah? Because we have stoichiometric coefficients of 1. Yep. Good. Anything else? Okay.
I thought we had to do KP because they were gases.
Okay, so the question is, so we kind of did this already for our N2O4 forming NO2 example. So we have our rate laws, we rearrange the equation, and we know that the rate of the forward reaction equals the rate of the reverse reaction, and so we can set all of that, this part, equal to K sub C. We're basically saying this is how we define K sub C. Okay. Check something real quick. Yeah. All right, so let's look at another example. Let's start thinking about a molecular picture of what's going on at equilibrium. So here we have a diagram that's showing a reaction going to completion. When we say going to completion, that means it reaches equilibrium. Each molecule in this diagram represents 0.1 moles of that molecule, and the volume of the box is 1 liter. All right, so if we're going to use concentrations, if there's one molecule, it's going to be 0.1 mole per liter. So if we let A be the red spheres and blue be the blue spheres, write a balanced equation for this reaction. So take a minute and do that. So we should end up with A2 plus B forming A2B, everything in the gas phase. Okay. Everyone okay with that? Yes. Well, you don't know it's in the gas phase. I will tell you. It's in the gas phase. Yep. It probably doesn't really matter, to be honest. Yeah, you're right, it doesn't matter. Okay, so then, all right, but everyone good with that equation? Yes?
Why is it like yield A2B when the A2 there's like on the right side there's an A2 and a B that aren't?
Yeah, so why are these left over? Is that what you're asking?
Yeah, or like why isn't it also plus A2?
Oh, so why don't we also include the fact that there are unreacted species?
Yeah.
I guess maybe that sort of is the answer to this. They're just unreacted. There's still reactants in this box.
Oh.
And this is going to point out that the demo with equilibrium, okay, that we could still have reactants left over. And we don't have to write them on the product side. Okay. Good question. Okay, then so if we had A2 plus B in equilibrium with A2B, what is our equilibrium constant expression? Take a look at the 4 options there. All right, and we should end up with A2B as a product divided by A2 times B. Those are our reactants, so C would be the correct answer. Everyone okay with that? Yes?
So how would you know what the coefficient if you're just given one size?
How do you know what coefficient? So I think maybe the good approach to doing this would be to figure out what the product is. And so if we know that we're forming A2B, we can figure out what we need to combine to form that. So, so we have A2B here. That's going to be our product. These are unreacted, so we can ignore those. And so the reactant has to be A2 and B. And those, if you look at the equation now, it's balanced stoichiometrically. Yeah. Yeah, so start with the product, I think. Yeah, good questions, y'all. Okay, so we have our equilibrium constant expression. We'll use the C because that's why I've written it in my notes, but this could just be K. I tend to get sloppy here after a while and only write uppercase K and forget the C, just so you know. The C is, while we're on it, the C is referring to the fact that these are concentrations. When we have P, it refers to pressure. And oftentimes we just don't include the lowercase c because we are usually working in concentrations, and it's kind of a rare occurrence when we're working in pressures. So that's sort of where that comes from. Okay, so our equilibrium expression was A2B over A2 times B. So calculate K sub C. And let me do this. This box, the circled box, is our equilibrium box. And our equilibrium constant expression has to be concentrations of things at equilibrium. Okay? Take a minute there. Again, each molecule represents 0.1 mole, and we're in a 1 liter box. Yeah, this is good. Talk to your neighbors. All right. So the answer that you should get is 40. But let's make sure we're all on the same page about how we get that. Okay. Each molecule represents 0.1 mole per liter, because it's in 1 liter. We have 4 molecules of A2B in our equilibrium box. And so we'll have 4 times 0.1 moles per liter, so we'll have 0.4. We have 1 molecule of A2 at equilibrium, so that's 0.1 mole per liter of that. And we have 1 molecule of B at equilibrium, and so we'll have 0.1 mole per liter of that. And that should give you 40. So notice that we paid no attention to the box that was reactants, right? That doesn't come into play at all. Right? It only matters what's at equilibrium. Make sense? Okay. Okay. Okay, so we can use the equilibrium expression to calculate, we can use the equilibrium constant expression to calculate the value of K if we know concentrations of every species at equilibrium. So for instance, here we have the Haber process. Again, this is the formation of ammonia, N2 plus 3H2 in equilibrium with 2 NH3. If we have concentration of N2, H2, and NH3 at equilibrium, we can then calculate our equilibrium constant K sub C. Hi. And again, this is C. It gets sloppy here. I should have embarrassed Nick pulling that table out of the room. All right, let's see. And so I'm just going to plug in concentrations. Don't forget to square things where appropriate, raise it to whatever power you need to. And I'm just going to plug these in and then give you the answer. Make sure you are comfortable with these calculations on your specific calculator. So our NH3 concentration at equilibrium is 1.40 moles per liter. N2 is 0.3. That's raised to the power of 1. H2 is 0.90, and that's cubed. When you do all of the algebra involved with this, you should get a value of 8.962. So for KC. You'll notice that I haven't included any units. We usually don't include units on the equilibrium constant. There technically would be units present. We're not going to worry about those. That's a whole different class if you want to think about equilibrium constant units. take some physical chemistry courses. But for now, just know you don't need a unit on the equilibrium constant K. Are there questions on that setup of that calculation? Okay. We can also solve for various equilibrium concentrations once we know our equilibrium constant. So if we then, let's say we know our equilibrium concentration of N2, we know our concentration of H2, but we don't know the ammonia NH3 concentration. But we have a K value. We can set all of this up to solve for whatever reactant or product that we need to solve for. In this case, NH3. And again, watch those powers. So you're going to get to a point where you need to square root this. So we're going to have 0.6. Yes. And 1.8 cubed. And that is all equal to 8.962. And so when you do all of the algebra associated with this, you'll end up with an ammonia concentration of 5.51 moles per liter. Now we're including units because it's a concentration. Yeah, I didn't show all the algebra steps, but work on that. Let me know if I did it incorrectly. Okay. So what happens if we reverse the reaction? So we start with N2 plus 3H2 in equilibrium with 2NH3. But what if we write the reaction the reverse way and we say 2NH3 in equilibrium with N2 plus 3H2? We still write our equilibrium constant expression in the same way we normally do. And so we have N2 products, concentration of products raised to their stoichiometric coefficients, N2 times H2 cubed divided by the reactant NH3 squared. And you'll notice this is the inverse of the equilibrium constant we just used for this reaction, right? So if we reverse the reaction, then K reverse, we'll do R, is equal to 1 over K forward. Does that make sense? We're flipping reactants and products, so we flip our numerator and our denominator. And so if you know an equilibrium constant for a given reaction, so we calculated our K value for the formation of ammonia. If we want to find the equilibrium constant for the decomposition of ammonia, so we want to find it for this equation, we can do 1 over K forward. So that would be 1 over 8.962, which is equal to 0.1116. I'm leaving a couple extra digits here. Okay? So I'm calling the forward reaction the one where we take N2 plus H2 to form ammonia. Okay? So that's for the reverse. Make sense? Now, you are going to do some problems where you get to manipulate equations, rearrange them, manipulate the equilibrium constants. So I think that's what I have coming up here, yes. So I think your book goes through some of the derivations of these things, these manipulations. So again, let's go back to our N2O4 reaction. The reaction we saw at the very beginning where we have a colorless gas forming a brown gas, the NO2 gas. if for that particular reaction we have an equilibrium constant equal to NO2 squared over N2O4 and a value of 0.212 for K. If we reverse that reaction, our K is going to be, the new K is going to be 1 over 0.212. That's the inverse. But what if we multiply that equation by 2 for some reason? Okay. So now let's go back to our original reaction, N2O4 forming NO2. Multiply the whole thing by 2. So now we have 2 N2O4 in equilibrium with 4 NO2. Now our equilibrium constant is going to be equal to the value that we got before squared. And the reason is that we're basically multiplying K times K. All right. Now we've got, there's a total here of 4 NO2s in the numerator and 2 N2O4s in the denominator, which is this stoichiometry in this reaction. Does that make sense? So there are a number of rules that you should remember and work with when we're manipulating our equilibrium expressions. If we reverse a reaction, we saw this, we take the inverse or take the reciprocal of K. If we double a reaction, multiply it by 2, K is squared. We triple a reaction, K becomes K cubed. Okay, raise it to that power. If we half a reaction, K becomes K 1/2. Take the square root. Okay. And this is a good one. If we add the reactions together, you're going to multiply those K values together. That's essentially what's happening in this example, where we're saying N2O4 in equilibrium with NO2, 2 NO2, that reaction plus itself to get this. And so we're multiplying those K values together. Just come down. Thank you, everyone. Have a good day. So I do have an example. We can work through this. This is from your book. So I like this one. We'll work through it next time. But if you want to take a look at it, it's SAE 15.8 in your textbook. Are there any questions before you go? Yeah, one question. Hold up, everyone. One question. Go back to